So our circuit started in the MIMS book, and we wanted something that would be able to detect heat, in this case infrared, which is the same idea. And you see here there's a 741 op-amp, which we use as a comparator. And this is comparing two thermistors, essentially. One, T2, as you see pictured here, is our room temperature, and T1 is the one that's actually being heated up by a fire or some heat element. When T1 gets heated up enough, the resistance drops and the comparator, which is normally on, turns off, and the 9 volts can run across the LED, turning it on. So, to repeat again, when the thermistor is heated up enough, the LED will turn on. The original MIMS circuit that we built didn't work quite exactly as we had hoped, and whenever we heated up T1, the LED turned on as opposed to turning off. So we did some troubleshooting, and we realized that if we flipped the inputs of 2 and 3, that when we heated up T1, now moved to the right side into pin 2, the LED would turn on. So we had a little trouble with the resistors the first time we were trying to make this circuit, and we just used a bunch of random resistors. And then we asked Professor Bensky, why isn't this working? And he said, what resistance are your resistors? And we said, oh, we don't know. And he said that they should be the same so that when your thermistors are changed, they're sensitive enough to detect that change. So all of our thermistors and our resistors are around 10K. Our pot is adjusted such that it's right below the threshold value, such that our LED is off, and so when our thermistor T1 is heated up, our LED will turn on.
This is our final circuit setup. You can see here we have our potentiometer, which we have hooked up to pin number 2 of the comparator, and that is in series with T1, which is this thermistor out here, which we are going to be heating up. Our reference voltage is put into pin 3, which is set by this thermistor here, which measures the room temperature. So now, as we compare those two different voltages, if the comparator turns off, aka when we heat the thermistor up, the LED will turn on. Since T1 is connected to the potentiometer, we can also turn the LED on by adjusting the pot. I will show you this now.
Well, yes. It has a little bit of okay.
We've also added to our circuit a buzzer that will go off at the same time as the LED, so there's also a audio component to our alert system as well. So the way that we're interfacing our circuit with the computer is through the lab jack. We're doing this by, first of all, grounding the lab jack, and then we are going to make graphs of the analog outputs of the circuit, both at pin 2, which is the varying thermistor voltage, and at pin 6, which is the output voltage of our comparator. So we can see how the changing resistance of the thermistor impacts the output voltage of the comparator.
This is our LabVIEW code. This was Kara and I's first time using LabVIEW, so we had quite a bit to learn. You see in the top left here, this is our motor control for our car, which rotates the wheels so that it can escape the fire. Down here, the 4 orange lines and the corresponding boxes are graphs. One is our comparator output voltage as a function of time, and our other is our voltage in as a function of time. Over here is what is moving our cardboard piece so that it can block the fire from the thermistor while escaping. Here is the active fire evasion system. You see the cardboard barrier, which will swing up when the thermistor, located here, is sufficiently heated. Now Kara will heat it up. And we have the motors at a smaller speed for the wheels so that we can see it stop as it has done. And there's our lab view code, and you see the voltage drop for the comparator, and on the right the voltage in as a function of time.